In section 11.4, we're talking about comparison tests. So with this type of test, you take your new series that you don't know much about, but compare it to a series that you do know something about. So for our purposes, that would be a P series or a geometric series typically, because we know how those behave. Those are simple rules. So how do you do this? There's two tests, by the way, in this section. The direct comparison test that I'm going to talk about in this video, and then we'll do another video with the limit comparison test, which is actually my favorite of the two. But, you know, you'll find out what you like better. Direct comparison test is a very simple concept. If I have a series that's diverging, well, that's the second one, so we'll start with the first one. If I have a series that converges, and I have a series whose terms are less than the series that I know converges, then the smaller series has to converge. Pretty straightforward. Similarly, for the divergence, if I have a divergent series and I have another series which is bigger than it, then obviously if the smaller one is going to infinity, the bigger one also has to go to infinity. So, very simple concept. The issue, which makes this maybe sometimes a little bit trickier to do, is that it doesn't work backwards. Like if I have a series that diverges and I have another series that's less than it, that's not going to tell me anything, because something's going off to infinity, something that's smaller might still be going off to infinity, or it might converge, you don't know. And the other way as well. So you have to be very careful about the inequalities with this particular test. It's all about getting the inequalities right. Okay? So let me give an example. So keeping in mind what we're trying to compare to, first of all, we have to figure out what to compare to. Okay, so I'm just going to write that over here before we do our test. So our P series, 1 over n to the P, converges, out of space again, P greater than 1, diverges P less than or equal to 1. Our geometric series, AR to the n minus 1, whatever it is, converges absolute value of r less than 1. So where, by the way, thinking about it, back in section 11.2, it was really important that we got this in the form AR to the n minus 1, because we wanted to use that formula for the sum. Here, if we're just talking about convergence or divergence, we don't really care what the formula for the sum is. So if you start from n, whatever, it doesn't matter. The important thing is that the ratio that r is less than 1, absolute value of r rather is less than 1, to make sure that this guy converges. So those are best options for sort of thinking about what we're going to compare to. So let's say you have a series like this. Okay? And I'm going to start from n equals 2 because I want all of my numbers to be positive terms. Okay? Now, this we can integrate easily enough. So that's also an option. But what you can think of is, well, this is basically going to behave like 1 over n, right? Because the n is there, it's only an n. So this should diverge. But we have to show that, and one way we can show it is by comparing, right? So, but you have to think about these things, though, in terms of comparing the individual terms here. Now my an is 1 over 2n minus 3. I want to compare, and it doesn't really matter. We can compare to 1 over n or 1 over 2n. That multiplying, isn't going to make a big difference. Well, we're going to actually compare it to 1 over 2n, because we have to mess with the. So we're just going to compare it to 1 over 2n. Sorry, that's hard to see. I'm doing a little better there. Okay, so we're comparing to 1 over 2n. We know 1 over 2n diverges, right? Let's see here. I can pull out the 1/2, right? And this diverges because it's a p-series with p equal 1. Now what happens? So I know that 2n minus 3 is less than 2n. So when I reciprocate it, 1 over 2n minus 3, this is going to be greater than 1 over 2n. So my series here is greater than the series that we know diverges. Okay? So I can say it was greater than 1 over 2n and 1 over 2n diverges. So does my original series. Okay? Really, this is not written in a very nice way. Okay? I am going to maybe write it up a little bit better right now. These are our ideas. So I'm a little bit out of space. I want to keep that. So maybe what I would like to write then, if I am asked to explain my thought process, I can write this series diverges by direct comparison since 1 over 2n minus 3 is greater than 1 over 2n for all n. And this series, and we can start for 2 as well, 1 over 2n diverges, since it's the harmonic series, p series with p equal 1. Okay? So you may want to also put this work into your little explanation. In this case, it's pretty easy to see that that's true. If it's a more complicated problem, you might have to show the inequalities a little bit more. So, but this is sort of what I would expect, like on a test or a quiz, for you to write down what your work is, not just converge divergence. So write it down in a way that is easy to follow. Because that's our first example. And it turns out that what we were comparing to was actually this first thing, a p-series. Let's look at another example. You can guess what I'm going to compare my other example to. All right, so my next example, and that was the divergent series. The next example is going to be this guy. What do I have? 3 for the n on the top. 3 to the n over 4 plus 8 to the n. So our thought process here is just kind of very similar to the previous one. The real driving force here is the 3 to the n and the 8 to the n. When I'm up in high numbers of n, that 4 is not going to make any difference. So it's really just more or less a geometric series with r equals 3/8. Okay? So let's see. What can we say about that? Now we know, so compared to 3, let me put the sign, 3 to the n over 8 to the n. Okay, so that's 3/8 to the n. This converges it's a geometric series with absolute values. Okay, so how am I going to compare it? Now, since this is a convergent series, if I want my direct comparison to make any sense, this guy better be less than that. So let's see what we have. 4 plus 8 to the n is greater than 8 to the n. So 1 over 4 plus 8 to the n is less than 1 over 8 to the n. And if I multiply by 3 to the n, it doesn't make any difference. So I'll just write right here, 3 to the n over 4 plus 8 to the n is less than 3 to the n over 8 to the n. So since this guy converges as a series, and all these terms are less than that, this guy will also converge as a series. Okay, so that's the idea. So this is sort of our scratch work. Let me see how, now I'm going to rewrite it again a little bit better. Okay? So similarly to what I did, I'm going to write it this way. This guy converges by direct comparison. So you see I'm telling you exactly which test I'm using. Because 4 plus 8 to the n is greater than 8 to the n. So, and I'm going to skip this one. Get rid of that. So 3 to the n over 4 plus 8 to the n is strictly less than 3 to the n over 8 to the n for all n. The series to the n over 8 to the n converges because it's a metric series with all right. So that's my nicely written answer. I don't have everything like written all over the place. Okay. So that's 2 quick examples of the direct comparison test. Our first one diverged, so it was a greater than. Our second one converged because it was a less than.